So we know metals, right? They conduct electricity. Uh, they are pretty good at, making sure the electrons move around pretty easily. Then we know non-metals, right? Non-metals like rubber or glass, they don't, uh, you know, conduct electricity. They are poor conductors, but they have different kind of, you know, um, material properties. Then we have like insulators. Those are kind of like a non-metals too. But then we also have semiconductor materials, and these are special kind of materials. Okay, the reason they are special is because to your liking, you can make them work like conductors, or you can make them work like non-conductors. They change their properties as a function of different parameters, such as the temperature. We learned about light dependent resistors. We did a couple of experiments on it too. What was the relationship between the temperature and the light dependent resistor, like light intensity? When the light intensity increases, it actually decreases the resistance of the light dependent resistor. So there was an inverse relationship between the lights and the light intensity. Similarly, we had a thermistor, right, in one of the lab. Thermistor, when the temperature increases, the resistance of the thermistor decreases. So again, there was an inverse relationship. But if you look at that thermistor, it will look like orange kind of material. And that orange material is basically cadmium sulfide. And that cadmium sulfide is a semiconductor. Okay. Similarly, if you look at photocells, they would have like an orangish, reddish color. And they are also semiconductors too. So cadmium sulfide is a semiconductor that is used for making thermistors or a photoresistor, which is also known as light-dependent resistors. Okay, so semiconductors are a special class of elements having a conductivity between that of a good conductor and that of an insulator, and that makes them extremely unique. Materials commonly used in the development of semiconductor devices. So what are the semiconductors? Almost everyone in the class would know silicon, right? Most of our computers, or some of these chips, integrated circuits, they are basically made on silicon wafer. And I don't know if you have ever seen a silicon wafer. It's a very, very tiny, thin sliced wafer, and it looks like grayish in color depending upon how thick it is. And then we also use germanium. It's again a very widely used semiconductor material. Gallium arsenide is a compound, also a very important semiconductor in the world of electronics. There are more semiconductor materials, such as which are the compounds of indium, gallium, phosphide, and arsenide. Okay, so for example, there's another semiconductor compound, gallium, indium, phosphide. This is another very important semiconductor materials. You guys must have seen a lot of solar panels in Massachusetts. All these solar panels are made up of semiconductors. Okay, the most widely used semiconductor materials for these solar panels is cadmium telluride. Okay, and also silicon is also very widely used. If you see a panel which looks like bluish in color, that's probably a silicon polycrystalline. Okay, kind of like this color right over here. If you see like a chocolate color solar panel, it's probably cadmium telluride, which looks like brown. And depending upon how much light it is, sometimes it may just look black from a distance. Okay, so these are the important semiconductor materials which are widely used. How do we choose like whether we're gonna go with silicon or germanium or gallium arsenide? Again, depends upon the application. There are various other factors. You have to see whether it is available on the crust of the earth, the abundance, how much is the cost in order to get the 100% pure silicon. Okay, the process is extremely not time consuming, extremely effective, and cheap and affordable. Okay, because if these process costs go up, the device cost also go up. Okay, so covalent bonding in intrinsic materials. Covalent bonding means basically two elements bonding together. And I'll show you one example over here. Um, Atomic structure of silicon, germanium, and gallium arsenide. So if you look at, you have silicon over here. Silicon has, I think it has a 14. Yeah, it has 14. And look at the valence electrons. How many valence electrons? That's got 1, 2, 3, and 4. Correct? It's got 4 electrons in its outermost shell. So if I ask you, can silicon combine with silicon to make a very strong covalent bond? What would be the answer? Yes or no? Remember, in a outermost shell, you need to have at least 8 electrons. Remember, we learned from week 1. Right now, silicon has 4 valence electrons in its outermost shell. So a silicon would combine with silicon and have a covalent bonding and have a very stable atomic structure. What's going on here? What do you see over here? You have this silicon, okay? This is again the atom, right? This is a nucleus. So it's a parent atom. And you got these dots here. And how many of those are? You got 4 dots. And each of this is linked with another parent atoms of silicon. So what is going on here? So the reason we refer to it as covalent bonding is because this silicon over here needs 4 electrons to complete its 8 electron in its shell in order to be stable. So what it does, it basically borrows or basically share 4 electrons from the neighboring atoms. So it's getting 1 from this, it's getting 1 from this, it's getting 1 from this, and it's getting 1 from this. So it's got 4 already, and then getting 4 here, from the neighboring atoms, completing 8 electrons, and then becoming stable. Okay. So similarly, it's same thing phenomena over here, same thing phenomena going over here. Everywhere, silicon having 4 electrons, and then pairing up with the 4 electrons in the neighboring atoms, completing its orbit with 8 electrons, and that makes them very stable. Similarly, if you look at over here, okay, gallium has 31 electrons. And then if you look at the outermost shell, you got 1, 2, and 3, okay. Arsenic has 33 electrons. And then how many in the outermost shell? 1, 2, 3, 4, 5. So what can happen here, folks? What can happen here? Gallium got 3 electrons in its outermost shell. Arsenic got 5 electrons in its outermost shell. Can gallium give away these 3 electrons to arsenic, and then those electrons can be over here, and then they make a complete shell with 8 electrons and become stable, right? And that's exactly what's happening over here. You got this gallium over here. You have the gallium over here. It's got 3 electrons in its outermost shell. And all of these electrons are shared by arsenic over here. So arsenic got 5, 1, 2, 3, 4, 5. It needs 3 more electrons, 1 each from gallium, and then it makes a complete orbit of 8 electrons. And that's what the covalent bonding is. Okay, that's what covalent bonding means. And when we combine gallium and arsenide, they make a semiconductor material, and that can be used to make solar panels or light emitting diodes and things like that.